Okay, welcome to the today's class. Our today's lecture is, so it is a lecture number 4. So we have been discussing about the modeling styles in Verilog HDL. Let us recapitulate what we have studied so far, and then we'll go forward. Okay. So in the last class we have discussed about the behavioral modeling. How do we write a Verilog program if the circuit is in the form of a functional table? Okay. So a brief discussion about each and every modeling style that we have seen. Today, let us take another example for the more clarity. We will write the same modeling styles for that particular digital circuit. So let us consider, for the simplicity, I'm considering one half adder. Sorry. For simplicity, I'm going to consider one half adder. Consider A, and this is called B. This is called sum. This is called C out. Those who haven't understand this one concept clearly in the last class, just look at now. How do we do this one? It is in a half adder, right? So this is the top level representation of your half adder. Okay. So let us write the first one is gate level modeling. Similarly, we are going to write data flow modeling. Thirdly, we want to write behavioral modeling. Let us see all these things at one shot. Okay. If you want to model any digital circuit with the help of these modeling styles, one common factor is there. That is external view. Okay. The external view is common. External view is common for all these modeling styles, right? So therefore, I'm going to write the external view of this thing. Okay, what is the external view here? Nothing but module. What is the name of this module that we have given here? Half adder, HA. And what are the variables we are using? A, B, sum, C out. Right. Okay. Now, another information from the point of external view, we need to declare which variables are inputs, which variables are output. Input and output I have written. So it is possible to write the output here also. After semicolon, that means the statement is completed. We can use another statement, output, S comma C out. Therefore, there is a provision is there. So once the semicolon is we have used, so that means this input statement is completed. Therefore, we can write another statement also adjacent to that one. Okay. And finally, we need to write AND module. Right? So therefore, this is the common for these three modeling styles. Are you agree with me? Okay. Therefore, I'm going to use use the same program. Okay, for the purpose of I'm going to copy in all these styles. Paste it here. This no. I'm going to copy all these things. Okay. Copy. Sorry, paste it is there. No? I need to copy this one. Copy. And then paste here. Okay, so this is the same. Okay. Similarly here also the same. So that you will understand for all these modeling styles, the external view is the same. Is it clear to all of you? Okay. The external view for the gate level modeling, for the data flow modeling, and for the behavioral modeling is the same. What is the difference here now then? Internal view is different for the different modeling styles. Okay. So what are the statements that I should use for this one? In the gate level modeling, I'm writing here is gate primitives. Okay. Gate primitive statements are required. Are you agree with me? It requires gate primitive statements. What are the statements here we have to use in the data flow modeling? So Boolean equations are required, or I can say that simply instead of saying that Boolean equation, assignment statements is the best thing. Assignment statements. Okay. What are the statements we have to use in the behavioral modeling? Everybody knows that. Procedural statements. Is it clear to all of you? So in gate level modeling, we have to use the gate primitives. In the data flow modeling, assignment statement we have to use. In the behavioral modeling, procedural statements. Okay. Now, let us write, depending upon your half adder, we are going to write what do you mean by the gate primitive statement, what do you mean by assignment statement, what do you mean by procedural statements, right? For the simplicity, for the sake of simplicity, I'm going to copy everything here. Copy, and I want to paste it here. Okay, fine. Now, so let us write a gate primitive statements. For the gate primitive statements, the circuit diagram is required. So what is the circuit diagram that we need to know about the gate circuit? So I don't want to use this one. So instead, I'm going to write some statements here based on based on gate level circuit. So let us write a gate level circuit here. So for the half adder, what is the gate level circuit? One exclusive OR gate is required, one AND gate is required, and this could be the sum signal, this could be the Cout signal. The inputs are A is one input signal, B is another input signal, and for this one A and B. So this is what the circuit diagram is, right? So we need to write the program for this one. So I'm going to reduce this size. Okay, now fine. So in order to write a Verilog program for this one, I'm going to write the name of this gate is G1. This is called G2. I'm writing, and I'm going to call this these gates into your main program with the help of the keyword called XOR. XOR is a keyword. The name of the gate is G1, for example. What I should write then? First, I should write output. Okay, what is the output here now? Output is yes. What are the inputs here? A comma B for the exclusive OR gate. I hope everyone can understand this. Similarly, we have an AND gate. So I have to use a keyword called AND. The name of this gate is G2. And what are the variables I'm using there? I'm using Cout is my output. First output I should write. A comma B I should write. So that's all. So this is all about gate level modeling. Are you agree with me? So depending upon the how the gates are connected, that information I need to put it here. So simply it is in a half adder, therefore it consisting of only two gates. There is no intermediate signals that is available. Therefore directly I am writing XOR and AND gate without using whiles. Clear? That's it. Next, let us see. Now, Let us see the data flow modeling. So we don't want to use, we have to write the assignment statement here. How do I write an assignment statement for this one? So module. So what are the assignment statement I should write? I need to know the Boolean equations for that one. Okay, what are the Boolean equations that are required for this one? Boolean equations are S is equal to A XOR B, C out is equal to A and B. Okay, this is what we need to know about the internal view of your design. Okay, so therefore we have A input here, we have B input here, we have some input here, we have C output here. Okay, now I need to write assignment statement, right? So I have to use assign here, assign. Okay, what I want to assign here, for the sake of some signal, I need to assign. What I should assign, A is XOR with B. So this is one continuous statement. Okay, so this symbol is actually an Verilog operator. Okay, and I have to use another assignment statement, assign Cout. Cout is equal to A and B. That's all. So this is the behavioral modeling. Sorry, this is the data flow modeling, right? So finally, we need to write N module. This is also very clear to each and every one. Okay. Now let us write another modeling style that is called behavioral modeling. So I have to write a behavioral modeling. For example, here I want to write N module. So what should we know about this one? What is the fundamental that is required for this one? That means a functional table is required. Okay. So for a half adder, what is the functional table? For example, here is my top level view. So it consisting of signal A, B, sum and out. Okay, if it is 0, 0, sum 0, carry 0, 0, 1, 1, 0, 1, 0, 0, 1, sorry, it is 1, right? It is 1, 0. If it is 1, 1, it is 0 and 1, right? So having the inputs are A, B are the input signals. We have some signal, we have C out signal. Clear? Now I need to write this functional table in the form of a procedural statement. Okay. The procedural statement. How do we do this one? Let us consider. So I'm going to use one of the important procedural statement is case statement I'm using, right? So for that, if you're writing the behavioral modeling, it is essential to note that one important statement called always statement I should write. Always, we need to find the changes of a particular variables, which are nothing but a sensitivity list. The sensitivity list tells us that the output is depending upon the variations of particular variable. That means output is changes only when there is a changes of the input signals. Therefore, input signals are treated as a sensitivity list. Okay, so available inputs are A and B. Available inputs are A and B. If there is a change in A or if there is a change in B or simultaneously A and B changes at the same time, the output will changes. Then only this particular block must be executed. Okay, begin and end block must be executed. So in between that one, we need to write a procedural statement. So what is the procedural statement I'm using here? In the last class, we discussing about case statement, right? So I'm using the case statement. Case, each and every possible combination we are treating as one case. This is the one case, second case, third case, fourth case, right? But A and B are individual signals. I need to combine these two input signals. Why we need to combine all these things, we will see later on. So for the combining of A and B, I have to use concatenation of A and B. Concatenation is nothing but curly brackets, which means that two individual signals are treated as a combined signal. Okay, so therefore it is possible to write one case is 2 bit of 0 0. So therefore this is what we can write. So if the 2-bit of 0, 0 stands for first variable that we are, first input vector that we are talking about. If this is the case, what it has to do? Sum signal must be sum is equal to 1 bit of 0, okay, and Cout is equal to 1 bit of 0 again. So if this is the case, this is the output has to produce. Okay, so therefore here I am going to use, since two statements I am using, here I am writing the begin and end here. Okay, so let us write another statement. Let us write another statement. What if 2-bit of 0, 1 is there? If that is the case, I should start begin. Some signal should be equal to 1 bit of 1, but Cout is equal to 1 bit of 0. So finally, and then finally, we have to end this statement, right? Okay, so let us write another statement. Let us write another case. So 2-bit of 1, 0, if this is the case, so I need to start begin. Sorry, it is a keyword. Therefore, it's for differentiating, we use another color. Begin, S is equal to 1 bit of 1, Cout is equal to 1 bit of 0 again. Finally, we need to write and here to complete that statement. Here we have to use another statement that is called 2-bit of 1, 0. So, sorry, it is 1, 1, right? It is 1, 1. If it is 1, 1, I can start begin. S is equal to 1 bit of 0, but Cout must be equal to 1 bit of 1. So this is how we need to write the Verilog program in. We have to write Verilog program in behavioral modeling. Okay, and default statement is also there. We write the default statement. Default. What if other cases? Normally we treat that for two input combination, for two inputs, two variables are there, we have only 4 possibilities are there, but more number of possibilities are also there. We will discuss that point later on. Okay, so let us start begin. S is equal to, I want to say that all are zeros. Okay, for the simplicity, 1 bit of 0 for default cases, right? So this is how we need to write a Verilog program in the data flow modeling. Okay, the same module, the same digital circuit is described in different ways. This is called styles, the modeling styles used in Verilog HDL. Is it clear to all of you? Is there any doubt? Please raise your hands, or maybe you can type it on the chat box, therefore I can discuss that point. Yeah, one point we forgot here. We have started the case, we have to end the case, right? So we need to write end case. So don't use the semicolon for end case and end module, okay? Not necessary, okay? But remaining statements must be ended with semicolon. After always also we should not use the semicolon. Here the semicolon should not be there, right? Always at the rate A and B, brackets are closed, but we should not write any kind of semicolons there. Okay, fine. Is it clear to all of you what we have done so far? Any doubts?
Yes, sir.
Yeah, if you have any doubt, please type it in the chat box. If not, I will go further. Not defined, this is a default. It is a default. So somebody is asking that it is a default statement. So why we need to write the default statement, we will see later on. Okay, so because we have all the possible combinations we have incorporated here, since as you asked that, I'm telling you briefly, since Verilog is a 4 value logic, that means for every input it takes 4 possible combinations. Therefore, if you have 2 variables, it's not it's not about 4 combinations, it's about 16 combinations. Okay, what are all the 16 combinations we will see in the coming classes. If you talk about that one, it will be difficult for you. Okay, fine. So any other doubt? How to write the code? Okay, no doubts. So from this section also you should tell if you have any difficulty, please let me know. So if you know how to write a Verilog program by using these 3 modeling styles, 90% of the Verilog programming language is very simple. Okay, these are the fundamental or basics we can call it as. Once you know this information, that is more than sufficient. Just only what are the different ways that we can internal modules, internal circuit will be writing in the internal circuit is in a different fashion we will see in the next class, in the coming classes. But overall, this is the concept of Verilog programming. Okay, only these 3 essential modeling styles are there. Of course, the structural modeling is also there. I will tell you later on what do you mean by structural modeling and all. But essentially, we have a behavioral modeling, data flow modeling, and gate level modeling. And very important to note that everyone should know that whenever we are talking about the gate level modeling, so we should know gate primitive statements we have to use like AND gate, OR gate, okay, NAND gate, NOR gate, something like this. So these things we will see later on. Okay, something else. If you are using the statement, Boolean equations are required. Boolean equations. So in the procedural statement, we should know that. What are the procedural statements? If statement, if else statements, case statement, etc. Okay, this you should know. So we will discuss about each and every individual modeling in the coming chapters. Okay, but everyone should know this one. Very, very important concept now. So here I forgot to write end modules, didn't, here end module. Here is the end module. It's missed somehow. Okay, fine. So far, so good. Now, the next question is, why should we, what we should do with this particular HDL programming? Okay, so far we have seen that somehow we have done HDL programming. That means we have described a digital circuit, okay, with the help of this language. Clear? Now, so now this is an input for simulation tool. So once we have described, that means whatever the idea is there in your mind, you have described something like this. Once your idea is correct or not, that need to be verified. Okay, that means we need to verify the functionality of that particular digital circuit. In order to do this one, we have to do simulation. Therefore, whatever idea is there in the form of a language, that we have to give it to the simulation tool, and simulation tool will verify whether you have whatever the idea that you want to write, whether that is correct or not, it will be verified. So this is called functional simulation. People will call it as functional simulation. I can write it here. Functional verification, or I can say that functional verification. So let us see what do you mean by functional verification and all other things now. Now, another another important use of this HDL code is that it is possible to generate the hardware. It is possible to generate the hardware. That means we need to do synthesis. We need to do synthesis. So we have to do the synthesis. So what is the synthesis here? Actually, whatever we have written here is a textual information. HDL is a text format. It is in the text format, right? So this text format is converted into an hardware. So what it will produce? It will produce a gate level netlist, or I can say that gate level circuit. So somehow we have whatever your idea is there, that is in the form of language that you have written, that must be realized by using the synthesis tool. Okay, so this one also I will discuss about later on. Okay, how the code is converted into a gate level circuit or gate level netlist, how it is converted in this one, we will see later on. For the time being, we are mainly focusing on simulation. Okay, somehow we have written the code here. So that code is correct or not, or that code is whenever you are giving some set of input signals to the design, whether it is producing the correct output, is giving the correct output or not, we need to verify. So therefore, it will produce in the form of a waveforms that it can produce, or text information it can produce. Text format also it is possible to produce as an output signal. Is it clear? So whatever we have described in the form of a Verilog language, that is the input for the simulation tool, that is input for the synthesis tool. So normally these are all the CAD tools that we are using. Okay, as we have seen in the previous classes, we told that. So all these things are nothing but CAD tools. These are all CAD tools. Computer aided design tools. So therefore we are not doing manually. With the help of computer and software, we are going to do this kind of thing. Okay. Now let us consider exclusively for simulation. Let us look at exclusively for simulation. Okay. Now the topic of discussion is simulation. What is the formal definition of the simulation? Verifying the functionality of the design. Verify the functionality of design. What do you mean by the functionality of the design? For example, we have a half adder here. We have input A, we have input B, we have some signal, we have Cout signal, right? So what do you mean by verify the functionality? As we know that before generating the half adder, we know the functionality of the half adder. What is the functionality of the half adder? A, B, sum and Cout. We know the functionality. What is the functionality? 0, 0 apply. We need to get output is 0, Cout is also 0. 0, 1 if we apply, 1, 0 is the output. 1, 0 apply, 1, 0 will be the output. 1, 1 you apply, 0, 1 will be the output. So this is the functionality of your digital circuit, right? We know the functionality of the digital circuit. Okay. So therefore, whether this hardware, whether this described program is providing the same output or not by applying these input signals, that we need to verify. Okay. So yeah. Yeah, this is the correct output only, that whatever I have done. Okay, now what I'm going to do here is that I'm applying here is A is 0 now, B is 0. So the simulator is doing something like this, taking the inputs A is equal to 0, B is equal to 0, and it is applying on the half adder program. Okay, and it should produce sum is equal to 0, carry is equal to 0. This is the task done by the simulator. And it takes another input, 0, 1 it considered. So another input it is applying, 0, 1 input is applying to this half adder. And it has to produce, it is processed within the half adder, it has to produce, next output is 0, sorry, the next output is 1, the next output is 1, this must be 0. It has to produce in this way. For example, if you are applying the 0, 1, if you are not getting 0, 1, 0 is an output signal, if you're not getting, then we can say that it is functionally wrong. Whatever you have described circuit is there, that is functioning very wrongly. Okay, it is not working properly. That's what we have to think about it. Once it is not working properly, we have to go to the program, we modify the program, right? Similarly, when you apply the 0 1 here, 1 0, if you apply, the sum value must be 1, carry must be 0. It has to produce. Okay, and if you apply the logic 1 here and logic 1 here, it has to produce 0, and this should be the 1, right? So therefore, this is the responsibility of the simulation tool. Is it clear to all of you? Okay, so what is there inside of the what is the fundamental behind this one is that whenever we want to verify the half adder, whatever may be the design it is, okay, we have to apply the input signals to that particular half adder. Okay, inputs we have to apply. Okay, 0 0 0 1 1 0 1 1 we have to apply to this HDL program, and finally it will produce an output in the form of a, as I mentioned, that output is in the form of waveform learner avachu. It is in the form of waveform, or it is in the text format. I will show you what you mean by the text format, what you mean by the wave format with the help of tool. Is it clear to all of you? So this is what the entire process we can call it as, simulation. This entire process we can call it as simulation. Is it clear to all of you? What do you mean by simulation? Verifying the functionality of the design. How do we verify the functionality of the design? First, you have to describe your digital circuit, and then we have to apply the inputs, and we need to identify the outputs in the form of a waveform or in the form of a text format. Right. So the question is, how do we apply the input signals? That's important. How do we apply the input signals to this one? For example, if you go to the laboratory, once the circuit is there in the breadboard, if you want to verify the functionality of the circuit, what we have to do, we have a switches are there, LED switches unte kada. So by switching logic one, just switch on to that one, and that will be applying the logic 1 to the circuit. We switch down if you put it there. Then what it says that logic 0 that we are applying. That's what the meaning of this one. So therefore the switches that we are using, physically switches are available, then we are using the physical switches to apply the input signals to the digital circuit. But now in this particular scenario, we have to write the input information also in the form of a language. Clear? We are applying the input signals to the digital circuit. All the inputs must be represented in the form of a language. Okay, so that is called Testbench. What do you mean by the Testbench here now? Testbench is nothing but provide the input information in the form of a language. Provide the input information in the form of a language, as simple as that. Okay, so I have mentioned that the input signals are something like this. Inputs are represented normally represent A is equal to 0, something like this table format that we have done. Okay, but in reality what we can do is that, let us see something like this. A is something like this. A. So 0 certain amount of the time, and B is also 0 certain amount of the time. Okay, after some time A again 0, after some time A is again 0, but B is 1, logic 1. After some time A is equal to 1 for some time, but B is equal to 0 for some other time. After some time A again remains the same, logic 1, but B is logic 1 here. So this is how a truth table is represented in this fashion. Clear? So therefore what we are doing here, it is a logic 0, logic 0. Logic 1, logic 0. Logic 1 here, logic 0 here. Logic 1 here, logic 1 here. Is it same that of the truth table? So A is 0, 0 certain amount of the time. B is equal to 0, 1. Sorry, next one is A is 0, B is equal to 1. So something like this. Next third one is 1, 0. Suppose 1, 0 is available here. Fourth one is 1, 1. 1, 1 I'm applying here. Something like this. So this information we have to write in the form of a language. I can simply say that this is also a description of a waveform. So the description of a waveform is also done with the help of Verilog language. Okay, the description. Description of waveform is done by Verilog again. So Verilog initially we have used it to describe the hardware. Am I right? Now I am going to describe the waveform also. Okay, so that's what. Let us see how do we describe the waveform with the help of Verilog. Here also we have to follow some syntax here. Okay, please carefully understand. So this is also, we treat this is also a simple module. Okay, so whatever the test bench, or I can say that this is for the simulator, this is, we can call, normally people will call it as a top module. This is called as a top module. Okay, so the top module we are representing as a module. So it is a module. So what we want to test, actually, we want to test half adder, right? We want to test half adder. Okay. So for that one, I need to write the name of this top module is something like this. Half adder test. Simply I'm writing half adder underscore test. Something like this I'm writing. And you should not apply any kind of input and output signals for the simulator. Okay, so that means that the simulation is nothing but a black box. We consider the black box name is half adder underscore test, HA underscore test. Whatever the name that you are, if you are interested to give, you can give there. Okay, and now another thing is that whatever the half adder program that we have done, whether it is in the behavioral, whether it is in the gate level, whether it is in the data flow, it doesn't matter. What is the external view that we have considered? So the external view inputs we have written there, right? So that inputs are represented as register data type. That we have represented as a register. That are A, B. See, simply I'm writing that. What inputs we have written, right? So in the previously what we have written there, it's comments. So if you write in the double comments here, something, 2 lines, if you write something like this, it becomes a comment. It does not affect this line. Okay, this register A, B does not affect. So initially what we have done, input and rasing kada, input A, B rasing kada. When you are writing the test bench, so replace the input with the help of the keyword called register. Clear? So this procedure you follow, and this information we will know why we need to, why we have written the register, reg keyword, all these things we will see later on. Okay. The next one is we have written the output, right? Output must be represented by wire type. Okay. Wire data type. Therefore, wire is actually sum comma cout. Okay. So that means here also, for the sake of simplicity, I'm writing output sum comma cout. Output, in the output, I have to replace the output with the help of wire. Okay. Now we have to call whatever the test that whatever the circuit that we want to test, we have to call that module. We have to call that one. So that means what is the name of this module that we have given there? You can see here, what is the name of the program? So here HA we have written, right? HA we have written. Okay. So I have to call that one HA. I want to verify that one, right? HA that I have to call. HA, directly the name that I'm using. The name of the module is M1, like gate 1, G1, G2, G3, something like this. And we have to write how the inputs and outputs we have given. So how inputs or outputs we have given, see here is A, B, sum, cout, right? A, A, B, sum, C out. Same manner that we have to write. So don't forget to write the similar fashion. Okay, if you miss that one, it's the wrong output will produce. So first one is A, second one is B, third one is S, fourth one is C out. So that's how I have written. So this is the module that I want to test. So you can see here also. So that means I am calling this half adder, right? In this diagram, I am calling the half adder. Okay, first I have given the half adder. Now I need to write this waveform. I have to write this waveform. This is the first step. Please remember, this is the first step. This is the second step that we have to remember. This is the third step that we have to remember. The fourth step is we have to write the input vectors. Input waveforms we have to write. Okay, let us write the input waveforms. Input waveforms are represented by using the initial statements. Initial keyword that I have to write. So initial block that I have to use, initial block, initial begin and end here. Initial block that I have to use to describe the waveforms. Okay, so let us write what is the half adder here is A and B. First, A is available at 0. Okay, that is 0. So therefore, that means something like this we are writing. Then x-axis we write it in the time. Okay, let us write the x-axis. Time we can write 0 nanoseconds, 1 nanosecond, 2 nanoseconds, 3 nanoseconds. I have written something like this. Okay, at 0 nanoseconds of time, what I'm writing here is that at 0 nanoseconds of time, the delay is represented by a symbol that I have to write. 0 directly we can write 0. If 0 nanoseconds of time, what do you mean by A? A is equal to 0. Here it is possible to write directly A is equal to 0, B is equal to 0. No need to write number format. Okay, if you write the number format, 1 bit of 0, it is possible to write. In the test bench, we have a provision. Directly we can assign A by 0, B by 0. Okay. So after 1 nanoseconds, for example, after 1 nanosecond, what about A and B? A is nothing but 0 only, but B is equal to 1. So the semicolon I'm writing. So this is the one statement, this is the one statement, this is the second statement. Okay. So after one statement, another statement is separated by semicolon. Or you can write in that one also. Now possibilities there. The third one is if you use another 1 nanoseconds, if you want to get the 2 nanoseconds here, we have to add another 1 nanosecond, not for 2 nanosecond directly. Okay, therefore it becomes 2 nanoseconds now. So the delay is added from previous value to the next value. So if you want to get the succeeding one, we have to add this delay to this one. So therefore, here the current value of this one is 2 nanoseconds. It becomes like that. Please remember. Right? Fine. Now, A is equal, now here in this case, A is equal to 1 at 2 nanoseconds, but B is equal to 0. Another 1 nanosecond, that means 3 nanoseconds. Another 1 nanoseconds. Okay, therefore we can write A is equal to 0. Sorry, A is equal to 1. B is equal to 1 again. Is it clear to all of you? How I have described the waveform? This is the way that we have to describe the waveform. Okay. But in addition to this waveform declarations, we have to write necessary information above this one. Okay. So, and another important thing is that, okay, once we have described the waveform, and we need to write how do we look at this waveform? It is in the form of a textual format, right? Text format, I want to look at the output. So for that one, for output purpose, I'm going to use another initial statement. Initial. I'm going to write a statement called $monitor. $monitor. This is the keyword. So we will discuss that. What do you mean by this one? $monitor. I want to monitor time, $time that I have to write. For the For simplicity, just take it as granted. This information we'll discuss in the coming classes. Time I want to look at, and then I want to see my output signal. A is a percentage of B. I think this is the scanf statement like in C language. A is equal percentage of B, and the binary format we want to display, and B is equal to percentage of B only I want to display, and some signal also percentage of B that I need to write, and C out is also a percentage of B. Okay, so these are the signals. Now I can write it as all these signals are represented by A, B, sum, and C out. Okay, so for the sake of simplicity, I have written in the down, but we have to write adjacent to that one. Okay, I hope people have understand this one. So the monitor statement. What is the monitor says that? So it will give you the textual format information about the A, about the B, about the S, about the C out. So this particular initial statement or this particular monitor statement is executed whenever there is a change in A, or whenever there is a change in B, or whenever there is a change in A and B simultaneously. Okay, this particular monitor statement is always executable whenever there is a change in A and B and C, sorry, A and B. So whenever there is a change is occurred, monitors that change, and it will produce an output signal. Okay. Next, another important statement is we have to use an initial statement. Therefore, we have to use an initial statement. We need to stop our simulation. We need to stop our simulation. For example, 3 nanoseconds ki ayipotundi kada, oka 10 nanoseconds ki off chedam, or otherwise 4 nanoseconds ki off chedam. At 4 nanoseconds, $stop we have to use. Simulation will stop at 4 nanoseconds. Finally, we need to write end module. So these are the very important things that we should know. Okay, this is the fifth statement. This is the fifth step. This is the sixth step. Okay, how many steps are there in the test bench? We have to follow 6 steps. Whatever the program, whatever the test bench it is, doesn't matter. We have to follow these 6 steps. So if you should not miss any one step while you are writing the test bench. Okay, module declaration, and convert the input and outputs in the form of a resistance of white data type, instantiate the component, and describe the input vectors, and we have to see the output in the form of a text format with the help of monitor statement, and I need to end the simulation by using the $stop, and I have to go for end module. Okay, whatever the digital circuit, if you want to test, this structure is common. Okay, only change is that, for example, depending upon your application, we have to instantiate the component instead of the half adder, maybe full adder you can call. Okay, for the full adder, 8 combinations are there. We have, instead of 4 combinations, we need to write 8 combinations. Okay, in the monitor statement, whatever the variables we are using, those variables we have to write. And the simulation is end depending upon your the length of the input vectors. Finally, we have to end the module. Okay, so this is how we have to give the information to the simulation tool. Okay, so therefore, for the simulation tool, what it is required? For the simulation tool, we require HDL programming, and we require test bench. So we have to give the test bench to this HDL, and the simulator will perform the simulation. So this is what the required for the simulator. I can say that I think better to write in this way. So in this way, for example, if you want to write a simulator, for example, you consider a simulator, it requires HDL programming, and it requires test bench. Okay, and it will produce output in the form of a text or waveform. Is it clear to all of you what we have done so far? If you have any doubt, please raise your hand. అర్థమవుతుందా మీకు? What the simulator has to do? Simulator has to take the inputs from the HDL programming, take the information from the test bench. It will process the code by applying the test vectors, and it will produce an output signal. Okay, so this is what the first step you have to do in your design. First we have to describe, second we have to do simulate your design. Is it clear to all of you? In the design process under the FPGA design, in the FPGA design process, what we have to do, first step is we have to describe the digital circuit. Okay, we have to describe the test vectors, what we need, and we have to simulate that one. Once the simulation results are correct, then we have to go to the next step. Okay. So, so far so good. If you have any doubt, please raise your hand. Otherwise, I'm stopping here. And tomorrow's class, we are going to see what do you mean by the synthesis. Okay. So this lecture is